So I'm pleased here to do show and tell. Let me first tell you something. So, about a year and a half ago, I had a sabbatical. So 2024 to 2025, I was in sabbatical, and I was trying to think, what am I going to do on my sabbatical? And so this probably happens, most of the senior people here, especially in astrophysics, may know this. When you're a graduate student or postdoc, you do all the calculations yourself. But then as you become a more senior scientist, you start to have students and postdocs, and then they do stuff. And one day you wake up and you realize, well, if my grad students disappeared, I wouldn't be able to do anything because I don't even know how to log on to the computer. And so I thought maybe I should spend a year trying to learn how to program a computer and do all the things that my students and postdocs have been doing for me for years, just in case. You never know. The other thing that happened about the same time is that I was somewhere, I can't remember where, and I heard Peter Lepage saying a few things, giving a talk. And does anybody know who Peter Lepage is? There you go. So Peter Lepage is a very eminent lattice gauge theorist at Cornell University. And he said that when he was young and he went to Cornell University, Ken Wilson was there. And I'm sure you all know Ken Wilson is one of the most astoundingly original and impactful minds of the 20th century in theoretical physics. He said that Ken Wilson had this, would always say that if you understand a physical system, you should be able to put it on a computer and get it to calculate for you. And so those two things, the desire to try to be able to do what my students and postdocs have been doing for me, as well as that basic idea that if you understand something, you should really get a computer to do it, sent me off to do things that I hadn't done before, which is actually some numerical work. So I haven't put gauge theory on a lattice. What I'm going to talk about today is the 1 over r squared force law, but still, I'm not Ken Wilson, so I do the best I can. So before I talk about what I'm going to talk about, I'm going to shamelessly advertise recent work that was done in collaboration with two people in this room, Nino, who is a first-year graduate student, and Cora, who was once a first-year graduate student. And I am like so thrilled with this work. So the basic idea is that if you read the gravitational wave literature these days, you will see lots of paper where people talk about lensing of gravitational waves. So there can be a merger of some black hole, supermassive black hole, stellar mass black hole. And if there is some massive object along the way, it could be that the signal comes via two different paths. But as the picture here shows, I can use my hands, as the picture here shows, the wavelength of a gravitational wave is big. So when we see images being lensed with electromagnetic waves, the wavelengths of electromagnetic waves are microscopic even on a human scale. And so on the cosmological or astrophysical scale, they're absolutely negligible. And so light rays propagate along straight lines. But the gravitational wave has a wavelength that is comparable to the Schwarzschild radii of the things being merged. And for LISA, that could be 10 to the 7th solar masses, or for, LIGO-type black holes, mergers, tens of solar masses. And then it can be lensed, perhaps by a dwarf galaxy that also has a mass of 10 to the 7 solar masses, or by, for LIGO-type events, an object in the Milky Way or some other galaxy that has a mass of several solar masses. So the wavelength is not necessarily extremely small, and so you have to take into account wave optic effects. And in order to take into account wave optic effects, you wind up having to calculate this diffraction integral, which is a function of some frequency of the gravitational wave, W, scaled to some appropriate physical scale, and position of the lens on the two-dimensional sky. And that diffraction integral is this integral. And it's just an integral, but it's an integral over a two-dimensional plane. And it is an exponent. It's an exponential of a complex exponential. And so these are very rapidly oscillating functions of position y on the sky and x that you're integrating over. And here psi is the projected gravitational potential. So to make a long story short, this is a real pain in the ass to evaluate numerically for all the frequencies, low and high, that you might be interested in, and for all the positions on the sky. And clever people have, over the past few years, developed very powerful codes to evaluate these very rapidly. But we had this insight, and I won't go through the math, you can look at the paper, that you can rewrite this integral as a two-dimensional Fourier transform. And so you can evaluate this as a function of y position on the two-dimensional plane for some given frequency as a two-dimensional fast Fourier transform. And there are techniques. We don't use the Fourier transform alone in physics. This is actually something that people make money off of. And so there are powerful techniques developed for Fourier transforms. And so it turns out that you can do this integral over the entire two-dimensional plane for all of the range of frequencies that you might be interested in extremely rapidly on a regular computer, on a high-performance computing cluster. And so this is the state-of-the-art code prior to our work. And this is our work. This is the computational time as a function of the number of positions on the two-dimensional plane. And you can make pretty pictures, which is fun. So if you have any questions about that, you can ask Cora and Nino and or me afterwards. But now, the subject of my talk is dark matter, and in particular, a new approach to understanding or studying dark matter dynamics under certain cases. So, as you know, this is a fairly knowledgeable audience here, I'm sure. There's a lot of dark matter in the universe. If you look at any galaxy in the universe, and you measure the velocities of outlying stars or gas clouds or dwarf galaxies or globular clusters at large radii, large distances from the center of the galaxy, what you see is the rotation curve. The velocities continue to rise rather than fall as 1 over r squared, as you would expect if the visible matter was all that there was. So we know from these rotation curves that there is a lot of dark matter in the universe, and in particular, a lot of dark matter in halos, very extended halos that surround galaxies. If I say anything incorrect, please stop me. And if I don't hear anything, I'll assume that I haven't made any mistakes. So we also know there's a lot of dark matter from lensing, as I just described. So this is an iconic picture from the early days of the Hubble Space Telescope. It was made by Andy Fruchter, who is a scientist at the Space Telescope Science Institute, actually one of my favorite scientists there. And there is a galaxy cluster that is lensing a bunch of galaxies. So what you're seeing, these arcs here are galaxies behind the galaxy cluster that are being lensed. And you can very clearly see those arcs. And again, by modeling the mass distribution in the galaxy cluster, you find that there's a lot of dark matter. So some of these galaxies are foreground galaxies in the galaxy cluster, but as you can see, there aren't a whole lot of them. And so most of the stuff there, most of the dark, is dark matter. We've invested a lot of money and effort over the past several decades to measure fluctuations in the cosmic microwave background and measure the distribution of galaxies in the universe. We'll hear more about this later on. Not everything is perfect, but with some very good confidence, we know that the density of non-relativistic matter, omega m, which includes dark matter and baryons, is bigger by a very statistically significant margin than the baryon density. So this dark matter is not baryons. It's not the stuff that we're made out of. It is something else. So we know a lot about dark matter. We are sure that there is a ton of it out there. We know how much there is in the universe as a whole, and through measurements of lensing around galaxy clusters, individual galaxy lensing, galaxy dynamics, we also know how it's distributed within the objects like galaxies and clusters in the universe. It does not emit or absorb light, so it's not ordinary baryonic dark matter. We don't know what it is. All the measurements, now here I'm going to summarize a lot of study. All the measurements that we have made and all the observations that we've made of galaxies, of galaxy clusters, of large-scale structure, the cosmic microwave background, are consistent with the notion that the dark matter has no non-gravitational interactions. The only way it interacts with anything else in the universe, including itself, is through Newton's laws, G m1 m2 divided by r squared. Except, and again, we might hear some of this about this later on in this workshop, except possibly for dwarf galaxies, some dwarf galaxies. So depending on who you talk to, you might find people who study dwarf galaxies who tell you that the structure of observed dwarf galaxies is not consistent with dark matter that has some non-collisional properties. And of course, it should go without saying that since we don't know what dark matter is, the canonical assumption that it has no non-gravitational interactions is just a base model. Just about anything that we can think of that might constitute dark matter will, at some level, have some interactions with itself and or ordinary matter beyond purely gravitational interactions.
Which properties of dwarf galaxies are in conflict potentially with being purely gravitational?
I'm not going to tell you that. You can ask me, but no, I'm not going to tell you that. I just want to motivate. The only purpose of the slide is to motivate the notion that we should be thinking about the possibility that dark matter does something more than just gravitate.
Sorry.
Yep.
Could the core cost problem also teach us something about the interaction of dark matter?
Yes, that's another motivation for considering the possibility that dark matter has something beyond gravitational interactions. Okay. You're here for the Swampland. I probably don't need you to do a whole lot of convincing. So here's the picture of the Tim Tate man. I thought this was the Swampland, but apparently Swampland is something different. So there are the theories of dark matter. At most, one of these is correct. So the default dark matter model is collisionless, but as I just said, we need to understand the implications of models that might have, in which dark matter particles might have some additional properties. So what I'm going to tell you now is how we model the galactic halo, a dark matter halo around the galaxy. So the simplest model of a dark matter halo is that it is spherically symmetric and that it has a radial density profile that is monotonically decreasing. It's a maximum at r equals 0, and it goes to 0 at very large radii. That is the simplest model of a dark matter halo, and it is held together by its own self-gravity. Dark matter halos are small compared with the cosmological distance scale. The typical velocities are 200 to 300 kilometers per second, which is 1/1000th that of the speed of light. And so these are non-relativistic objects. And if they're non-relativistic objects, then we can describe the gravitational field generated by this mass distribution rho of r in terms of a gravitational potential through the Poisson equation. Or equivalent, and equivalent to this is the statement that the acceleration on any body that moves in the spherically symmetric dark matter density distribution is radially directed. So it points towards the origin, and it is minus the derivative of the potential with respect to the radius. And this is equivalent to the statement that the acceleration that any particle moving in this potential experiences is equal to minus Newton's constant times the mass at smaller radii divided by r squared, the distance from the center. And the mass at smaller radii is simply an integral of the density r squared dr times 4 pi. All good so far? When you look at orbital, planets orbiting the solar system, the simplest pictures, they show you that they're circles. The more, realistic ones show you that they're ellipses that close in on themselves. The most general orbit, though, in a spherically symmetric gravitational potential is a Rosetta orbit. It's an ellipse that does not necessarily close in on itself. So the orbit of each particle moving this dark matter potential looks something like this. And each dark matter particle has two constants associated with it. One is the energy, if it is a static halo, and the other is the angular momentum. So particles that move in spherically symmetric potentials have a constant angular momentum. And so each orbit, the orbit of each particle, looks something like this, and it is characterized by an energy, an angular momentum, and also the plane of the angular momentum, the plane of the orbit. Now, turns out that there's a very interesting math problem, since this is a Center for Mathematical Sciences, it should be noted. There's a very interesting math problem, which is the following. So each particle moves on an orbit of a given energy and angular momentum that looks something like this, but it moves in that the orbit is determined by the potential that it moves in. However, the potential is generated by the distribution of all the particles, or of all of the orbits. And so there's a mathematical self-consistency that needs to be achieved here. So the potential is determined by the distribution of all of the orbits. So f of E comma L is called the distribution function. So it tells you how many particles there are with a given energy and angular momentum. And if we make the simplest ansatz, just to keep, to start things easy, if we assume that this distribution function depends only on the energy, not on the angular momentum, then the density at any given point r is going to be equal to the mass of each particle times an integral over the velocity distribution at that given point r of f of E. Okay? But the energy here of each particle is 1/2 the velocity squared times the mass plus the mass times the potential energy. So it is equal, so you can rewrite this integral here as v squared dv, change from b to e, and rewrite the integral like this. Okay. So the density at any given point r can be written as this integral over here, which can then be understood as a function of the gravitational potential, since the radius and the gravitational potential have a one-to-one relation. And it turns out, so this is an interesting mathematical exercise, this formula that gives you rho in terms of f can be inverted to give you f as in terms of rho. So if I have rho, for any given density profile, I can calculate the gravitational potential, and once I have the gravitational potential, I can determine this distribution function that gives rise to that potential. So it turns out there's this remarkable fact. The two-body problem is solved. In fact, I solved it last week in my classical mechanics class. But it's been solved. That's not the first time it was solved. So the two-body problem we understand. The three-body problem we can't solve. But the n-body problem, where n is a bazillion, is solved. So this is beautiful. The problem has been solved, and now we have a complete mathematically consistent theory for dark matter halos. However, what happens if there's new physics? What happens if these particles have something beyond purely gravitational interactions? So for example, and this was the original motivation, suppose I have a dark matter particle that can decay to a lighter state and then emit a dark photon. So suppose I have a dark matter particle that weighs 100 GeV, and it decays to another particle with a mass of 99.5 GeV, and then emits a dark photon. In that case, so delta m divided by m divided by v squared, so I have a very small mass difference between the heavy and light particle. In that case, when the dark matter particle decays, in its rest frame, it gets a velocity kick. So if this happens to one particle out of the 10 to the 60 particles in the galactic halo, if this happens to one particle, that particle moves from the orbit that it was on into some other orbit. That means that the distribution function changes. That means that every single other particle in the system is going to also react to it. And so even if one particle decays, the mathematical self-consistency is destroyed. And if lots of the particles decay, then everything changes. These particles decay, when they decay, that kinetic energy boost, that velocity kick they get, is effectively heating the halo. And as the halo gets heated, it's going to expand and evolve. And as it expands, the orbit of each particle will change. And as the orbit of each particle changes, the potential changes, and that further affects the orbits of every other particle. So this beautiful self-consistency goes completely down the toilet if dark matter particles decay. It also goes down the toilet if I have, dark matter particles decay to two massless states that, exit, that leave the system. In that case, the mass of the system is simply decreasing with time. And if the mass is decreasing with time, the potential changes with time. If the potential changes with time, the orbits of all the particles change with time. And again, the mathematical self-consistency goes down the toilet. If I have self-interacting dark matter, and lots of people write papers about self-interacting dark matter. So if two dark matter particles can scatter either elastically or inelastically, then again, that scattering redistributes the orbits, the energy and angular momentum, and changes the distribution function. And that again will alter the evolution of the system. I think I said this, they could be elastic, inelastic. Suppose for some reason you believe that Newton's constant will change with time, then again, the potential is changing with time, the orbits are changing with time, the mathematical self-consistency is no longer valid. And then there might be some some astrophysical things that happen. Suppose you have a galactic halo and somehow matter is added to it. Then the potential will change, the whole system will evolve in some way. Or suppose you have a dark matter halo and you remove some of the mass, if it's tidally stripped. Then the remaining particles are moving in a gravitational potential that has been altered, and so the orbits will change and everything goes down the toilet. So the way people have treated this in the past is one of two ways. First of all, there are Fokker-Planckish type things. And in any of these systems, you can typically understand, roughly speaking, what's going to happen by waving your hands and just thinking a little bit. But if you want precise results, if you actually want to see what's going to happen with the controlled calculation, then what people have done is n-body simulation. And an n-body simulation is a brute force solution to a difficult problem. So what you do is you simulate a self-gravitating system. You approximate, instead of having 10 to the 60th dark matter particles, you assume that you have 10 to the 6th dark matter particles, or as many as you can put on your computer. Typically 10 to the 6th is a reasonable number that people use. And then what you do is you set up the initial conditions. You give each particle a position and a velocity consistent with your initial spatial and velocity distribution. And then at each small time step, you look at each particle and each of those million particles, and then you calculate the 1/r² force with the other 10 to the 6 minus 1 particles, and then you sum that 10 to the 6 minus 1 number of forces to figure out what is the force, the acceleration of this particle in this time step. Then you do that for all million particles, and then you advance the whole system forward by one small time step, and then you do that over and over and over. Okay? So people do these, and typically when they do it, you use a supercomputer because it's a big calculation, and typically it takes a lot of time. 24 hours on a supercomputer, typically. And the thing I never have enough of is patience. So the reason I started to think about this years ago, I wrote a paper with Annika Peter and Chris Moody where we did this. And we used up a lot of supercomputer time, probably more back then than we would use today. But we calculated the evolution of the density as a function of radius for dark matter density profiles in which the dark matter was decaying. And we did simulations for a variety of decay, so velocity kick that the particle gets in decay, and lifetime for the decay. So we did it. But people all continue to do this. So here are a few recent papers from the literature on the evolution of dark matter halos when you have self-interacting dark matter. So here's an abstract. You can read it. The abstract is so long, it could use an abstract itself. But what I want to point you to is not the results, but the acknowledgements. And the acknowledgements include performed on computational resources managed and supported by Princeton Research Computing. Princeton, as you know, is a very wealthy university, and so they have a lot of money to spend on research computing, and they used it. Here's another paper by another of the top groups working in self-interacting dark matter, including my former collaborator, Annika Peter. Again, they have an abstract, 10 to the 5 simulation particles, 10 to the 4 particles, n-body simulations, and again, simulations of this work were conducted on Ohio Supercomputer Center, mostly on the CCAP condo. I don't even know what that is. Again, required supercomputer resources. But it turns out these calculations can be done much more easily. And in fact, all the calculations that they did that required 24 hours in a supercomputer, I can do on this laptop for the decaying dark matter in a couple of minutes, for the self-interacting dark matter in a couple of hours. So the basic observation is an n-body simulation is overkill if you are trying to study the evolution of a spherical system, because an n-body simulation involves the phase space distribution forward in 6 phase space dimensions. So 3 spatial dimensions, we have x, y, z, but then the velocity has 3 components, and so the phase space distribution is 6-dimensional. But in 3, if I have spherical symmetry, the phase space does not depend on all 3 components of x. It depends only on the distance from the center. The phase space distribution is going to be the same at all angular positions at the same radius. It then does not depend on all 3 components of the velocity. It depends only on the radial component of the velocity and a tangential component. And if we have spherical symmetry, that tangential component can be substituted or swapped out for the angular momentum. So you can actually write the phase space distribution in terms of 3 quantities, one of which is conserved for each orbit. And so strictly speaking, the phase space distribution, if the angular momentum of each particle is conserved, is only 2-dimensional. If the angular momentum can change by scattering, then 3-dimensional. The other thing is, if we have spherical symmetry, the acceleration on any given particle, the second time derivative of the radius of that ith particle, is simply the gravitational acceleration plus the angular momentum term. So the force on any given particle can be determined by simply counting the number of particles that are at smaller radii. So if I use this, if this I label here is simply the rank, the distance, if I just order all the particles by distance from the origin, with 1 being the closest to the origin and 10 to the 6 being the farthest from the origin, then this is just mass of each particle times I divided by that radius squared. This is the angular momentum of each particle, which is conserved, and r cubed. And so I don't have to do that n squared, I don't have to calculate n squared 1 over r squared force interactions. So we did this. We implemented it in a code. First, I did it in Python to try to teach myself Python. And then I got pissed off at Python. And so I asked ChatGPT to translate it to C. And then it did it, sort of. And then Chris and I have been working to actually make this a good code since then, reasonably good code. So we have a code that does this. So what we do is we generate a realization of n particles, where n is 10 to the 5, 10 to the 6, whatever you want. We give those particles radii and velocities that are consistent with some given distribution function. That's our initial conditions. Then at each time step, we advance each particle from the equation of motion that I just showed you, which is just a second-order differential equation. Then we reorder the particles by radius so that we can calculate the mass enclosed within the radius of any given particle. And then we iterate steps 2 and 3. And then we watch it go. So we've written a code. Chris has done most of the heavy lifting. Chris has learned how to use Claude and ChatGPT. He now has an army of AI agents working for him. So the code is available. Claude also made the picture. So since this is a mathematical sciences center, a little more. So what we're doing is we're taking a phase space distribution, f of x comma v, And we are calculating its total time derivative. The derivative depends on, first of all, partial with respect to t. There's then a partial with respect to x times the derivative of x with respect to t. And then there's a partial with respect to the velocity times the derivative of the velocity with respect to t. If the particles are collisionless, then the phase space of each particle is on the phase space density of each particle is unchanged. And so this equation, this Liouville's equation, is total derivative of f is equal to 0. The system does not evolve. In 3 spatial dimensions, if we have spherical symmetry, the equation gets reduced to this. So strictly speaking, V has a radial component and a tangential component, but in spherical symmetry, there's no acceleration in the tangential component, so there's no perpendicular or tangential perpendicular dot that shows up here. So it's a simple partial differential equation that we're solving by simulating the orbits. So here's a picture of the initial conditions for a simulation. It's not the whole thing because here I'm plotting the distribution in radii and total velocity, so I don't separate the radial and perpendicular components because that would be complicated to show on a 2-dimensional plot. So here is a self-gravitating halo where most of the particles are sort of, a few hundred kiloparsecs from the origin, and they have velocities of about 150 kilometers per second. And then here is a movie that shows how this phase-space distribution evolves. And it's evolving. So you can see there's like little wiggles because, at any given time, particles are moving in and out of different velocity and radius cells, but the overall distribution is unchanged. And now the code that we had as of a year ago had small energy changes. Chris has now figured out how to run the code so that the energy is conserved essentially to machine precision. Okay. So it's numerically, it's very stable. If we have a self-gravitating halo with no collisions, 10 to the 6 particles, 10 to the 5th particles, it'll go for hundreds of dynamical times without any noticeable changes. Next slide. Let me do that. Here is a plot of the orbits. So each particle has an orbit, but the orbit is circular. Sorry, not circular. It's a spherically symmetric. It's an orbit in spherically symmetric potential. And so the radius of each particle simply oscillates. So, particle in a nearly circular orbit, like this red one over here, stays at roughly constant radius. But then you see some here that are oscillating quite a bit in radii. Those are more elliptical orbits. And the density is actually, the number of particles in small radii is actually fairly small. Not only because the density, for this particular simulation, we took a constant density core, but also the volume in phase space is proportional to r cubed. So few particles at small radii. So here is a simulation, if I can get it to go. One of the first simulations we did. This is a simulation of what happens if dark matter particles decay. So this is the number of particles as a function of radius. So, most of the particles are at, a typical radius of about 100 kiloparsecs. And then what we do is we run the simulation, but now we allow each particle to decay. So particles can decay with some probability, exponential, at any given time step, some fraction of the particles will decay. And what happens is the following. It's kind of boring, but it's sensible. So as the particles decay, each particle gets a small velocity kick when it decays. And so those velocity kicks wind up heating the halo. And since a halo is a self-gravitating system, it has a negative total energy. And so if you heat it up, it becomes less bound and it spreads out. And so that's what's going on over here. And in this simulation, between the start and finish, about half of the particles decayed. Next simulation. This one is almost the same. So here is, I've got Newton's constant evolving in time. And we're going to have audience participation here. Is Newton's constant increasing or decreasing with time? got 50% chance of getting right. And if you turn on even a fraction of your brain cells, more than 50%. See, everybody knows the answer, but everybody is scared. Everyone's got imposter syndrome. So everybody's scared to say. Well,
Let's say decrease.
there we go. So Newton's constant is decreasing. The potential well is getting shallower. The thing is spreading out. Okay, I'll show you some more exciting movies momentarily. So these simulations, as I said, these were some of the first ones he did. Those took 10 minutes on the MacBook Pro. I think I can get this down to about a minute now with the current code. Next thing we looked at is self-interacting dark matter. And we did this in collaboration with Oren Sloan. So I spent my sabbatical part-time at the CCA, and Oren Sloan was still at the CCA. And I was working on this, and I went to his office just to shoot the shit. What are you working on? Blah, 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 self-interacting dark matter. I'm like, oh, that's interesting. Has anybody ever thought to do this? He said, no. So we did it. So for various reasons, motivated largely by the cusp versus core problem that may or may not exist with galactic halos and problems with dwarf galaxies, people have entertained the possibility that dark matter particles might scatter from each other. And if they scatter from each other, then if I start with a dark matter density profile that is an NFW profile that goes as 1 over r at small radii, then the particles in the very center are very cold. And so if they can scatter with particles that are coming in from further out, they can heat up. Okay? So you can have heat transport between these cold inner parts and the slightly warmer median parts. And what happens is that cusp then disappears and you get a constant density core. Okay, that's the expectation with self-interacting dark matter. But if you wait a really long time, then as those particles scatter, they wind up transporting heat out. So some particles get ejected to larger radii, but the particles that remain get cooled. And if they get cooled, they go to smaller radii, deeper in the gravitational potential. And so if you wait long enough, the heat transport that the scattering induces should give you a gravothermal collapse, where the density at the very center starts to become huge. And this is the velocity evolution that you expect. So in an FW halo profile, the velocities at the center are very cold. They'll thermalize. Then most of the particles get scattered out, but the ones that remain in this very highly dense core have a very large velocity. You get a larger velocity. So that's the expectation. Mathematically, we now have a right-hand side that's non-zero in the Boltzmann equation, a collision term. And it's very straightforward to put this into our simulations with equations that are complicated but correct. And I say that not just because Claude checked them for me. We also had 3 humans check, and all got the same answer. So here is a movie like the one I showed you before. Here's the number of particles as a function of radius. That is the initial distribution, and there are wiggles in here. I think we used 100,000 particles in the simulation. So those are just root n fluctuations. And we turn on self-interactions, and let me show you something. Let me stop it here. Stop. Okay, so I should say that, So we had an NFW halo. So the density profile was 1 over r, and so there were lots of particles at the center. And if you look at the very beginning, you'll see the number of particles in the center decrease. Okay, so that is the scattering out of the 1 over r density profile. Okay, you see that? It's a subtle effect on this plot, but you can see it. And then if I keep going with time, it sort of hangs around for a while. And then after a very long time, we start to get this gravothermal collapse. Okay. And there you have it. So now we have this gravothermal collapse, and we're seeing that highly dense core. These simulations, which were done last year when we wrote our paper, break down when that core becomes too big, because the scattering rate becomes very large and we can't resolve it. As of last week or 2 weeks ago, Chris now has a code that conserves energy precisely and can actually resolve the core. So what we actually are seeing now is what happens. So at some point, the core becomes very dense, but then it sort of reaches a constant density and then very slowly evolves after that. I can't show you that. Oh, wait, maybe. So Chris emailed me this morning. That might have been it. I don't know. I don't have it to show you right now. I might be able to show you later. I'm particularly proud of this plot. You're not going to believe this, but I made this. So here is the density profile as a function of time. And it looks like there's a lot of scatter, especially low radius, because there are very few particles in the simulation with 10 to the 6 particles. Very few particles are actually at very, very small radii. This is a log plot over here. So I'll just show you a few snapshots. Do I have the snapshots? I'll show you the snapshots in a second. Here is another cool movie. Here is the phase-space distribution for self-interacting dark matter. So here's a density core. If you look carefully, so this is the radius, this is the radial velocity. So if you look carefully, you should be able to see clumps going around this direction. Because if a clump has a positive radius, it moves out. And then as it gets to large radius, the radial velocity gets to 0, and then it becomes negative. And so each particle is moving in an orbit that looks like that. And strictly speaking, the density distribution should be perfectly smooth, but the root end fluctuations. So you can sort of see it. But then at the center here, so at the very early times, you see particles getting removed from the very center. But then with time, you see the gravothermal collapse. So the density starts to increase towards the center. Okay. Here is another movie of the inner parts of that distribution. So here I'm zooming in on the small radii. And you can see, the particles sort of thermalize and then hang around for a little while. But with time, you get heat transport that takes some of the particles from the inside, moves them out, and leaves the other ones going in at smaller radii. So there you can see the density increasing. What else? Here's the very center. Very few particles, so it's very noisy, but there you can see that gravothermal collapse. And as of a year ago, that was as far as we could go, but now we can evolve the system even after that dense core has formed and watch its evolution. Here is a plot of the number of particles as a function of radius. So this is the number of particles in the very, very center. So there's a few particles in that very center, and that 1 over r cusp very quickly decays, gets scattered out. But then there's a slow evolution. And after 300 dynamical times in the simulation, you see the formation of the gravothermal collapse. And then this part over here on the right, that's numerical crap. The plot that Chris showed me last week actually plateaus, as it should. Yep.
So, how fast are the particles moving right at the center or close to the center? Do you have?
Yeah. Ta-da! I can't do that for every question. So this is the, what the hell is this? Oh shit, is that nothing? Here it is. So this is the radial velocity squared. So early times, the particles at the very center are cold. This is for the innermost 0.2 kiloparsec. So we're smoothing over quite a bit of that core. So initially you've got cold particles. Very quickly they thermalize, and then the velocity stays reasonably constant. But as that core forms, it starts to become very large.
So does having super fast particles affect galaxy formation in any strange way?
The super fast is not, we don't see velocities. I don't think that there is any way that we can measure the velocities of dark matter particles except by assuming physics. But I don't think there's any observational consequences. I think, for some reason, the dark matter particles in our galactic halo are moving twice as fast as we think, but maintaining the same distribution, I don't think we'd know. But the dense cores, people do think may have implications for observations, the density, the high densities. And so here's the here's the snapshots. So the initial density profile was an NFW. So it goes as 1 over r at small radii, 1 over r cubed at large radii. Most of it's further out. And then very quickly, within the first gigayear, that self-interaction scatters these black particles down. But then after 15 gigayears, you start to see that gravithermal collapse. And at 16.5 gigayears, it's all the way. Yep.
I have a whole lot of questions, but it's really nice. But one question is, I mean, if you're really forming a galaxy, you really start with stuff really out there, and it's going to be self-interactions will matter even to form that initial distribution.
That's a good question. And I don't have I have an answer, but it's a complicated answer. So when we run our simulations, we assume that the dark matter has virialized. Our initial conditions are NFW profile, and then we see how it evolves. Yeah, right. You're right. That is not the correct. Yeah.
Another question is, can you have things spinning the proton? Absolutely. Because that's also going to. And the third thing is, I guess when you say self-interactions, I'm assuming you mean point-length self-interactions.
Yes.
Having some light media, or not so light.
I mean, as long as the range is short compared with the size of the galaxy, we can do it. But we can't do 1 over r squared long range. We can't do long range interactions.
Okay, so those are important constraints, right?
Yeah. So I should say this is not. The purpose of this code is not to model astrophysical systems. It is to understand the basic consequences of new physics.
So I guess what it would be saying is that in this case, you expected, but the question is, how did it form?
Yeah. So I have something about that. We said something about that in the next paper, which I'll mention, but I won't discuss.
You could, in principle, put baryons in this system.
Yes, and there's a guy named Rotem Barnea, who's a graduate student with Oren Sloan in Tel Aviv. And when they're not in the bomb shelter these days, they work on it. So there's another thing we can do, I think for the first time in history of humanity. So I told you that we made the simplest assumption that the velocity distribution was isotropic, the distribution function dependent only on the energy. However, in realistic gravitational collapse, you expect most particles in galactic halo to preferentially have radial orbits because the galaxy forms via gravitational infall. So it turns out that the most general distribution function for a spherically symmetric system can have also an angular momentum dependence. And it turns out, therefore, that for any rho of R, for any density distribution, there are an infinitude of distribution functions that can give rise to that one density profile. And so to try to explore how results might depend on that, we took 2 simple models. So one simple model, this is just cut and paste from the paper. You can have a distribution function that depends on energy and angular momentum that's L to the -2 beta times F1 of E. Okay, L here is the angular momentum of each particle. F1 of E has an Eddington-like formula that's a little bit more different that you can evaluate for any given rho. And so you can generate anisotropic distribution functions here, and beta is the anisotropy parameter. So if beta is 0, we get the same thing we had before, isotropic orbits. If beta is -1/2, then the orbits are preferentially tangential. If R is greater than 0, then they are preferentially radial, or vice versa. So you can set these initial conditions up. Another possibility is something called Osipkov-Meretz models, where you write the distribution function in terms of an f of q, where q is the energy minus angular momentum squared. The equations, and again, f of q is obtained by some Eddington-like formula. So we can run simulations where the initial velocity distributions are anisotropic rather than isotropic as assumed in all prior simulations.
Sir, can you explain why this?
Why what?
Why this particular combination of E and L squared?
No.
I think it's the effect of the function.
It's, yeah. Yeah, so I should say that here the anisotropy is 0 in the center of the galaxy, and then it becomes perfectly radial orbits at very large distances. So here the anisotropy parameter varies with radius. So here our initial phase space densities is the radial velocity radius. Here's what you saw before, isotropically distributed orbits. Beta equals -1/2. The radial velocities are larger. I got it backwards. Radial velocities are larger, beta equals 1/2. The radial velocities are smaller. These are more tangential or circular orbits. What's interesting, though, is that the difference between these models with different beta is not just in the velocity, the direction distribution of velocity at a given point, it actually changes the energy distribution. So these are various different models that all have the same density profile, and what's plotted here is the three-dimensional velocity dispersion. So the three-dimensional velocity dispersion for a Hernquist profile or an NFW profile at any given radius can be very different depending on whether you have anisotropy or not and how you introduce it. And we find that the collapse time, the time for gravithermal collapse, depends fairly significantly on your assumptions about the anisotropy. As does, well, there's not much more information here. The velocity dispersions also evolve. This is the evolution of the anisotropy. It's not too much of a surprise that once you turn on self-interactions, the anisotropy goes away fairly quickly. Brief advertisement, current work with Oren Sloan and Rotem Barnea, graduate student in Tel Aviv with Oren, Chris Sigurdsson, and Robert Caldwell. We are investigating what happens if only a fraction, F, of the dark matter is self-interacting. And Rotem has come up with numerical results and actually has a very nice analytic understanding of what's going on. You can try to see, there's other things you can do. Suppose you have an NFW profile and then you slowly grow a supermassive black hole at the galactic center. So people have studied this in the astrophysics literature, and you can simulate it very quickly with this code. And I'm going to close with what I think is probably to me, the most interesting application. So here what we did is a simulation where we generated some density profile for a self-gravitating system that extended out like this, and then I arbitrarily cut out the outer 40% of the particles. Okay, so I took away 40% of the mass, left 60%. And the reason I did this is the following. Suppose I have a star like the sun. We're going to find out if there are any stellar astrophysicists immediately. Suppose I have a star like the sun, and I magically strip the outer layer, just remove, the outer 10% of the mass, outer 1% of the mass, magically. What happens to the remaining star? Does it expand? Does it contract? Does it stay the same? If you say, I don't know, that is a correct answer. Okay, so does anybody know? Don't think about it. You either know or you don't. Okay, so stellar astrophysicists know this. And the reason is that if I have a X-ray source coming from a compact binary, so suppose I have, a black hole, this is a shitty drawing, and there's a companion star. So these are the equipotential surfaces in the rotating frame. So what happens is if I have a companion star that fills its Roche lobe, then matter gets transferred to this Lagrange point and then falls onto the black hole, forms an accretion disk, and then this emits X-rays. So most persistent X-ray sources from compact binaries, black hole or neutron star binaries, have a companion star that is overflowing its Roche lobe and therefore donating matter to the companion. And it turns out that there are two possibilities. If the star is convective, then the physics is such that if you remove some of the outer layer of the mass, as you do here, the star expands. And if that were to happen, then it would start dumping more of its matter, and there would be a runaway process, and you would not have a persistent X-ray source. In persistent X-ray sources, the companion star has a radiative envelope, which means, and if you have a radiative envelope, if you strip the outer layers, the physics is such that the star then shrinks very quickly and then slowly evolves back. So in persistent X-ray source, the star has a radiative envelope, which means that if you strip the outer layers, immediately it shrinks. And so I've always wondered, a star is a spherically symmetric, self-gravitating fluid. A dark matter halo is a spherically symmetric, self-gravitating system of collisionless particles. And I've asked for the years, anytime I run into someone who does dark matter, who does dynamics, I say, what happens if I strip the outer layers? And nobody has ever been able to answer. Now that we got this code working, we can run it. And this is what happens. Go. So that is an actual bona fide simulation of the evolution of a spherically symmetric dark matter halo after I've stripped the outer layers. And you see with time that it relaxes to something. Okay. And then Chris ran a higher resolution simulation and plotted the phase space.
So did it relax to NFW?
That simulation, it relaxed to a density profile that went very close to r to the minus 10 at large radii. And I don't know why, but we fit for that parameter, r squared to the alpha. Alpha was 4.98 plus or minus 0.02.
Isn't the system the kind of system that should give it? What's different about this than something?
So in this simulation, the initial density profile was not an NFW.
I know. Should
No, why? Because those guys say it should. Why? Nobody knows why it should be an NFW profile. So there you go. So in phase space, the phase space distribution, the density profile becomes smooth, but the initial structure, that sharp feature in the phase space distribution, remains preserved with time. So there it goes. Okay. So what else do I have? There's all kinds of things that you can do with this. You can study how spherical halos collapse and virialize, which that last movie was sort of an initial step towards. You consider particles of differing types and masses. You can finite and hard scattering. Well, we did that. Globular cluster evolution and mass segregation you can model this way. Self-gravitating system of stars and dark matter. Rotem is doing that. Inelastic dark matter, I think that one of Tracy's students is doing this. But he's not here. He's visiting Fermilab and doing it with people in Fermilab, with Gordon Krnaic and Asher Berlin. Other angular momentum, actually, this is an old slide. We did that. So the code is available to download. If you want to study funny dark matter properties, you're welcome to do so. And you can do it with your laptop. You don't need to apply for supercomputer time.